This leads me to the work-energy theorem, which kind of succinctly states what I mentioned on the last slide. Essentially, if you have done some work to an object, you have applied some force over some distance, and that work is going to equal a particle's change in kinetic energy. We kind of write this mathematically, as you see right here, where the total work that was done to a system is going to change its kinetic energy. The book tends to write this as K2 and K1. Essentially what you're doing is you're looking at a difference in potential energies, one at the second position and one at the final position. And what we're doing here is we're saying, okay, was the work done on a system going to be positive or was it going to be negative? And what that's going to do is that's going to change the kinetic energy. If the work that you did to a system was positive, then you have increased the kinetic energy. If you have done negative work to a system, then essentially you have decreased your kinetic energy. We can go ahead and use this work-energy theorem to go ahead and solve example 6.3 in the book, so you're following along. This is using the sled that was pulled by the tractor from example 6.2, where we had all the forces acting on that sled, where we had the mass and gravity in the downwards direction, we had friction in the backwards direction, and we had some normal force, and we went ahead and we solved for how much work was done by this entire system. Now what the problem is saying is it's saying, okay, suppose the sled was moving initially with this velocity right here. We've applied our force, we've applied it for 20 meters. What is its velocity at the end of the day? Some things that we know is we know that we did some work to this guy. We know that the total work done was going to be a positive 10,000 joules. We calculated that. Now we know the initial velocity. Something that the book does, which you should take a quick look at, you should be able to do this on your own fairly quickly, is calculate the mass of the sled is going to be 1,500 kilograms. What we can do is we can say, I'm interested in solving for this velocity right here. I can use the work-energy theorem and say that the total work done is going to be equal to the kinetic energy at point 2, that's this one over here, minus the kinetic energy at point 1. And I know what this guy is. I can solve for the kinetic energy at point 1. It's going to be equal to 1/2 mass times velocity 1 squared, and that's going to be 1/2 multiplied by 1,500 kilograms multiplied by velocity 1, that's going to be 2 meters per second, quantity squared, or equal to 3,000 joules. Now what we can do is we can say, I'm interested in this velocity 2, and I know that the kinetic energy at point 2 is going to be 1/2 mass velocity 2 squared. If I solve for my kinetic energy 2, then I can solve this guy's for velocity very easily. So I can rewrite my equation right here for kinetic energy 2. That's going to be the total work plus the kinetic energy 1. So total work was 10,000 joules, and the kinetic energy 1 was 3,000 joules. So the kinetic energy 2 must be equal to 13,000 joules. Now all I need to do is solve for my kinetic energy, or solve for my velocity squared. So here I'm going to say my kinetic energy 2 is equal to 1/2 mass velocity 2 squared is equal to 13,000 joules. So V2 is going to be equal to 2 multiplied by 13,000 divided by the mass, which is going to be 1,500 kilograms. And don't forget the square root. And at the end of the day, you're going to come up with 4.2 meters per second. So here we've used the work energy principle to solve for kinetic energy and solve for the final velocity of the block. And interestingly enough, we could have done this using Newton's laws of kinematics, where we write out our force, we calculate our acceleration, we know how far it was pushed for, and we would come up with the same final velocity. Example 6.4 uses the same type of thing, where we want to say that our total work done to a system is equal to its change in kinetic energy, K2 minus kinetic energy 1. If we were to draw the free body diagram for this hammerhead right here, we know that when it is falling, it's always going to have its weight in the downwards direction. It's going to have a little bit of frictional force associated with it, and its displacement and its velocity are going to be in the downwards direction. And kind of intuitively, you would say that the weight is much larger than the frictional force, so you would expect the net force to be in the downwards direction, in the same direction as our displacement. So we would say that our work is going to be positive, and in this case, having a positive work is going to increase the kinetic energy. And if we knew what the kinetic energy was right here, the book tells you what that is, we could figure out what the kinetic energy would be right here and solve for velocity. I expect you to come to class being able to solve this guy for velocity, simply following what or maybe not necessarily following what the book did, but solving on your own and checking your answers with the book using this work energy principle. If we consider what happens when the block hits the I-beam, then we're still going to use the work energy principle. Let us now draw our free body diagram for when the hammerhead is pushing on the I-beam. It still has its weight in the downwards direction. It still has a little bit of frictional force, and now it has this huge normal force that is not even to scale. And you can kind of in your mind's eye say, okay, I'm going to sum all these forces up. I know now that the net force must be in that direction. It's the motion is still in the downward direction. It's slowing down. This tells me that my net work is going to be negative because F and S are in opposite directions. What that means is it's going to slow my object down. It's going to decrease its kinetic energy. So make sure you're able to solve that before you come to class. We can take a look at example 6.5, and you might think that this is a trick question. What it's saying is suppose we have two ice boats and they're both initially starting from rest. Which of the two of those is going to finish or reach the finish line? Which one is going to have a larger kinetic energy, the blue boat or the red boat? And if we go ahead and write the work energy theorem, the total work done to each ice boat is going to be equal to its final kinetic energy minus its initial kinetic energy. We know that the initial kinetic energy is actually going to be equal to 0 because it's starting from rest. Each of these two boats had the same force put on each boat over the same distance. The angle between the force and the distance is 0, so the cosine of that angle is going to be equal to 1. So each of these two boats is going to have the same force and the same distance. However, and at the end of the day, they're going to have the same amount of kinetic energy. What's going to be different between these two boats is the blue boat is going to be going at a slower rate because it has twice the mass. This force had more inertia to overcome. However, both of these two boats are going to end at the finish line with the same kinetic energy, simply different velocities. Now it turns out that in the real world that many forces are not actually a constant, and this is where using work to solve these problems makes life a lot easier. What I want to do is I want to say we want to write our work is equal to our force multiplied by our distance, multiplied by cosine of theta. I'll say that that's equal to 1 just for this particular instance for simplicity. And if we look at our force and our displacement over here, where they've changed to x's just to help confuse you, if we want to calculate how much work was done by this varying force over this distance, what we can do is we can break this guy up into many tiny little delta s's and say that the work is roughly, or that the force is roughly constant over each one of these delta s's here, and say, okay, so for this particular delta s, my force is roughly a constant, and so I can write that the work that was done by this varying force is going to be equal to the force, now a constant. This one is going to be A, this one's going to be B, this one's going to be C, multiplied by the change in position at A, plus the force at B, also roughly a constant, multiplied by the change in position at point B, and so on and so forth. Do that ad nauseum, and we can calculate what the work was done by this varying force. If you've taken calculus, what we're going to do now is we're going to take these delta x's and assume them to be very, 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 very small, and so we would actually write our force is going to be the sum of all of these little tiny forces multiplied by the delta x, the position that we've broken our graph up into. And if we make these infinitely small, we would say that the work is equal to the integral of force, and now I'm going to add back in the angle dotted with some tiny little ds right there. If you have had calculus, then this makes absolute perfect sense. If you have not yet had calculus, then this might be a little bit foreign to you. This is what's going on behind the books. I'm not going to necessarily give you a varying force and say integrate it, but I just wanted to say that this is what's going on if we have a varying force. So I mentioned springs on the last slide, so let's go ahead and take a look at a spring. We can write the force that is required to stretch a spring to be equal to some spring constant k, as well as this distance x that you stretch a spring, or which is how far you've stretched a spring. Now this spring constant k, I've mentioned we call that the spring constant. That's an inherent property of each spring. It depends on the material that the spring is made out of, how many coils it has, and so on and so forth. And you'll see that value either listed for each spring. It might be 5 newtons per meter, or it might be something that you have to solve for. The units for this guy, newtons per meter, you can kind of see where that comes from to make this equation right up here work. That force is in newtons position is in meters, so the units of spring constants have to be in newtons per meter. And if we think about a spring and we want to pull on this spring, then the force that we have to apply to that spring is going to be the spring constant multiplied by how far we've stretched that spring. And you can kind of see conceptually in your head that you know that the spring is pulling back on you. So the force of the spring is going to be in the opposite direction, and it's going to have a magnitude of, the magnitude is going to be the same, the direction is going to be different. Similarly, if you take a spring and you push on it right there, and you compress it now by some distance x, then the force that was required to do that is going to be equal to the k multiplied by this distance x that you have pushed the spring. And now everything is in the negative direction. You have to keep those negative signs in your head, or say, now I've gone in the negative x direction, so my force is going to be in the negative direction. And kind of conceptually, you would expect that the spring is now pushing back on you now in the positive direction, and it's going to have a magnitude of the same as the force, which is kx. If we wanted to figure out how much work was done pushing or compressing on a spring, then if you've had calculus and you're not scared to see integrals, then the book walks you through how to go ahead and calculate how much work was done. Highly recommend that you do that. If you haven't had that, then we can simply jump straight to the result. The amount of work that is done to stretch or compress a spring is going to be 1/2 kx squared. And one thing to be careful of when it comes to the work for a spring is it going to be positive or is it going to be negative? And the work is going to be positive on a spring if the spring is, say, retarding the motion, or you are adding energy to the spring. The spring will be losing energy if it is, say, pushing an object away from it, or giving some of its energy into a force or into a velocity. We can consider bathroom scales as a simple spring problem. The older ones tended to be just simply springs. Now it's all piezoelectrics, but that's a different story. If you step on a bathroom scale, then it's going to essentially go down, and how far it goes down is going to depend on two things. It's going to depend on how much force you applied downward on that scale, and it's going to depend on that spring constant k. If we know how far we go down, in this case it's going to be 0.01 meters, and we know how much force we have, in this case it's going to be 600 newtons. That is also in the negative direction. If we define upwards to be positive here, we can simply say, Hooke's law would say force is equal to k multiplied by the displacement. We can go ahead and we can solve for what the spring constant should be. It's going to be 600 newtons divided by, it's going to be in the negative direction, divided by 0.01 meters, and we would say that our spring constant is going to be 6 times 10 to the 4th newtons per meter. And we can also say that we know that the force is in the downwards direction, and we know that the displacement is in the downwards direction, x, so we can expect that the work done on the spring is going to be positive. Recalling that work is equal to force dotted with displacement here. If force and displacement are in the same direction, then work is going to be positive. If they're in the opposite directions, then work is going to be negative. We can go ahead and calculate how much work was done on this guy by taking a look at the work energy theorem, only now we wouldn't be talking about kinetic energies. We would say that the total work done on a system is going to be 1/2 k x2 squared minus 1/2 k x1 squared. This is very similar to the work energy theorem that we saw earlier that said the work total was equal to the change in kinetic energy. What we're writing here is something very similar. It's going to be that the work total that was done is going to be equal to the change in potential energy of the spring. So this is not only the work done on a spring, but also its potential energy. And if we said, that our initial position x1 is equal to 0, and we know what our final position is, that's x2 is going to be 0.01 meters, and we know what our spring constant is, then we can go ahead, well, first let me say, because I know that x1 is equal to 0, then we can go ahead and say that the work done on this spring is going to be 1/2 k x2 squared. I know what my spring constant is, I know what my displacement is. I can go ahead and I can calculate that guy out. It's going to be 3 joules. So we can work spring problems we have two things that we can solve for with springs. We can solve for forces, we can solve for spring constants, and we can also solve for how much work was done, knowing a work energy theorem that applies now to springs, in addition to what we know already applied to kinetic energy. An interesting case could be where we start to merge the work energy theorems for the springs and for moving objects. We can do that if we consider an air track glider that has some velocity attached to a spring, as you can see kind of the sketch right here. We know that the force is going to be varying. This problem would be very difficult to solve using Newton's laws if I asked you to say solve for the initial velocity given some distance that this guy traveled. Now, if I draw the free body diagram for the cart, as the book has done for us down here, we're always going to have our weight in the downwards direction. We're always going to have our normal force in the upwards direction. The force of the spring is going to be in the backwards direction, and I know that my displacement is going to be in the positive x direction. So we can see, just looking at this, that the displacement and forces are in opposite directions. So the work done by the spring is going to be negative 1/2 k d squared, where d is going to be the displacement from the initial position. If I think about the movement of the cart, I can say that the work done by the spring is going to also be the work done to slow the cart down. At some point, we know that the cart is going to have a final velocity of 0. How much work was done to that cart in order for that to happen? The work done, thinking about the kinetic energy theory, is going to be 1/2 mass velocity squared, and it slowed the cart down. So the work is going to be also negative. It's going to happen in the opposite direction. Now what we can do is we can say the work done by the spring must be equal to the work done by the cart. So I could say negative 1/2 k x squared is equal to negative 1/2 mass velocity squared, my negatives are going to cancel out, and my 2's are going to cancel out, and now I have an expression, fix that guy with a D, and now I have an expression where if I know how far my object traveled, I can go ahead and I can solve for the velocity. The book actually gives you some velocities and so on and so forth. I highly recommend that you work this and you understand this problem before you come to class. Secondly, the book does it using friction as well. Make sure that you're comfortable working a problem like that where there's friction and a work energy theorem using springs and moving objects. Okay, I wanted to skip over that last slide because it's a little too complicated. Now let's talk about our last concept. This is the concept of power, and much like work had a very specific definition in physics, so also does power. And it turns out that power is the rate at which work is done, or we can write it power is equal to the work divided by the time. We can write average power as being some change in work divided by some change in time, or instantaneous power being, using the derivative. But really it's how much work was done divided by how fast you did it. Looking at work and looking at time, I know that the unit must be a joule per second, because work is in joules, energy is in seconds. This also has just a simple definition. We're going to call that to be equal to 1 watt. When you look at your light bulbs, you see things with watts. That's a unit of power. You might be familiar with horsepower if you're interested in cars, or you may have seen something like kilowatt hours on the meter outside of your house. So these are other kind of familiar units, but when you're working in SI, always work in watts. And essentially, if you consider, suppose I lift some box and it takes me 100 joules worth of effort to do that, then my power is going to be 100 joules divided by 1 second, or 100 watts. If I'm a little bit slower and I lift that same box, only now I do it in 5 seconds, the amount of work that I've done is totally and utterly the same. However, my power output is down by a factor of 5, only 20 watts. So if we know that the power is equal to some change in work divided by change in time, and we know that the work is equal to some force times a distance, we could also write this to be the change in force divided by the change in distance divided by the change in time. And you also can see change in distance divided by change in time is going to be a velocity. So if you follow the steps in the book, you can convince yourself that the power is related to the force and the velocity, written kind of specifically for the force being parallel and in the same direction as the velocity. A more general equation for power would be equal to the dot product of the force and the velocity. Again, this is a scalar product. What comes out of this at the end of the day is going to be a scalar. The power, much like the work, much like energy, is all going to be scalars, no direction associated with them. And if we know our forces and we know our velocities, we can go ahead and we can calculate out powers. Take a look at example 6.9. Convince yourself that you could solve a problem like that in class if need be, or even on an exam or something like that. I expect that you should be able to use and apply this equation come class time. Last but not least, let's consider example 6.10, and what we're looking for is how to figure out how much work a runner did as they ran up to the top of the world, to the top of the formerly known as Sears Tower, the Willis Tower in Chicago here. How much work they did is simply going to be how much force they applied multiplied by, not their distance, but by their displacement, or more specifically, the force dotted with their displacement vector. So here we have the displacement vector right there, starting at where she starts her journey and where she finishes her journey. Now, the force that she has to use, if I draw the free body diagram for the runner and assume she's going at a constant velocity, this is the force of the runner, and this is her mass times gravity. What I'm interested in is how much work was done by this force of the runner, and this force happens to be in the same direction as the displacement s, so I can say that this force must be equal to the mass times gravity. This is the force of the runner, constant acceleration, so mass times gravity. And rather than use an s, the book actually gives you a height, so s is equal to some height. Mass times gravity times height is how much work I had to do to run up the stairs, or she had to do to run up the stairs. It gives you some values. You can plug them in and come up with 2.17 times 10 to the 5th joules. You are, of course, following along with this example in your book. Then it asks you to calculate how much power it took, saying, knowing how long it took her to run up the stairs. We know that the power is equal to the work divided by the time. We know the time, we know how much work. Make sure you convert work or time into seconds, and work should already be in joules if you want to end up with watts at the end of the day. And last but not least, we can use how much power she does to figure out what her average velocity would be, saying that how much power she applied is equal to her parallel force multiplied by her average velocity. Make sure that you're comfortable working a problem like that before you come into class. I highly recommend that you work the problem and then you take a look at what the book did or what I do when it comes to solving these, so that way you know where your weaknesses are and are not.